and maybe we can just build a sample deck like that as well. So first things, do you have any prior experience with any SPICE tool? PSpice, LTSpice, a college day, anything?
College actually in BTech, I have used HSPICE. After that, I have not used. Yeah.
Okay, so you understand the basic concept of a SPICE tool, right? I mean, why we use it, like a circuit simulator. So yeah, so let me just display my screen. Some stuff ready, and then I'll just share my screen. Okay. Okay, I think this is. I will be showing my screen. Please tell me once it's visible. Can you see my screen?
No, not right now.
Okay. Is it visible?
Yeah. Like it's loading.
Okay. Okay, it's loading. Okay. Tell me once.
Okay.
Yeah, you can see it. Yeah. You can see it now, right?
No, it's coming blank. Black.
Oh. Okay, it's coming black.
Yeah.
Let me stop and start
Okay,
again.
now fine. Stop.
Okay.
Yeah.
Okay, came in. Okay, that means. Okay,
No.
wait, I stopped presenting.
Okay.
Yeah, I stopped. Okay, wait, yeah, let me keep it. So, actually, you can see it. Tell me, yeah.
Yes.
Blank for you?
No, again blank. Now
Okay,
it came.
is it yeah, okay, it came now, right? Okay. Okay. So basically what we do is, so see, as you may have maybe mentioned something.
Your voice is coming very low.
Our, what about now?
Yeah. No.
Yeah. So our PDN network is generally multi-stage. So there are multiple stages in the PDN network, and different stages will be modeled in a different way. And we use SPICE to kind of build the full power delivery network in one kind of one place, like kind of split different parts. So example, so if you see generally a PDN network, right? You can see my screen now. Can you see my screen? Yeah. So yeah. Okay. So if you can you see my pointer?
Yeah.
So let's see a PDN network starts like from the VRM. It has a bulk capacitor, which are the large capacitor values which are close to the VRM. Then to the motherboard caps, right? Some of them on the either on the top side or on the bottom side, right? And then we move to the package. where we have the package caps on the lower side, which is called LSCs, land side capacitors. Then we have some die side capacitance, as well as the actual die, right?
Yeah.
And on the die we also have some inherent MIM capacitance as well. C die it's called, or C die, MOS capacitance, die capacitance, whatever.
Okay.
So this is, so as you can see the red line is power. So as you can see the power transmission line, the power shape which goes from here. I mean, it's just a representation, but as you can see, it starts from VRM and goes to here. So what we are doing is generally is we don't model the VRM as such, because as PI engineers, at least in Intel, our job is after from the inductor to the full end, to the die. So what happens before the inductor, what is the VRM voltage regulator, we are not worried about that. That is handled by the PD team, the power delivery team, the board team. As a PI engineer, your job starts from the inductor. From the inductor till the die is your domain, where you will be doing most of the system work. Your job to ensure you meet the power specs in this region. So we only share an LVR or an RVR value from the LVR and RVR value from the PDT, which they will give you, depending on, and which they will provide you with.
Okay.
The second is we have to have the capacitors, right? So generally cap models, we kind of, so the whole PDN network, starting from, let's say, cap to the package top, right? We get this modeled via Power SI, right? So in Power SI, we load the layout, board layout, as I showed last time. We merge it to the package, right? We merge. What we do is we form ports on the capacitors, right? All the caps.
Yeah.
Then we form a port on the top side of the package, which are called bump ports.
Okay.
Where we form ports on the top side of the package.
Okay.
And this is which and this bump ports are where you hook up your die collaterals.
Okay.
This top. So which we had discussed in the previous calls, right? We had with Prasad and where we were looking at the sub-circuit, the die, whatever has been given by the vendor. So this is where you hook up the die collateral and all the die collaterals.
Okay.
So for the capacitors, why do we hook up only ports? Is we have our own models which are generated by Intel. Intel has its own model for all the capacitors.
Okay.
Depending on the value. Pankuri will share them with you. We have a tool from which we generate those models.
Okay.
Where we can get those models, and we hook up those models at the ports. So I will show. So then I will while we go into the deck, I will explain to you like what exactly I mean. Hook up the models.
Okay.
So this is how. So if you look a basic PDN network, right? So if you see, let's say in SPICE. So first thing is you have to give a, so if you let's say, so the thing is we use, okay. So HSPICE is like a command text driven tool.
Okay.
So if you go, I will open, it's like, see, PSPICE is a GUI based tool, right? You have a GUI wherein you can maybe click different components, click and drag, and you build your network.
Yeah.
Like you do that. But HSPICE is different. HSPICE is basically completely everything is driven through text. You actually build it via typing. I can show it to you, understand it.
Yeah.
So I will take, this one is fairly simple. Tell me once, okay, not this. Tell me once you can see a notepad file, the black background.
Yeah.
Can you see? Yeah.
Yeah.
Can you see my screen?
Yes.
Yeah. So, okay, I'll keep this to the side. First, we will explain here. So, as you can see, we will be providing a voltage regulator, right? We will voltage supply. Okay. So, in HSPICE, because so let's see, so because the example is HSPICE, because it's completely type, like it's text based, right?
Yeah.
So you'll build a deck like this. You'll be building a deck like this. You'll be making your connections. If you want to connect a register, you'll connect it.
So everything we have to give in
What
text.
it becomes
Yeah.
very
Like,
yeah, you have to give it text based.
okay.
Yeah. So what becomes very important is the node names. So that is very important for SPICE.
Node names.
Because then between which nodes do you want what component or what S parameter to be placed?
Okay.
So example, let us say we want to connect between, let us say in this node and this node, right? And there are 3 nodes I'm drawing, okay? And I want to connect the L. So I want to connect a voltage source, okay, VRM, and then I want to connect inductor, and then I'm going to connect a resistor.
Okay.
Right? So I will like A, and I will call this B, this node B. I'll call this node C. So when you want to like achieve this, right? So this is our aim, right? We want to build this simple RLC circuit. So what you will do is, so let's say first is if you want to place a resistor, you call R, okay? If you want to place an inductor, you call L.
Okay.
If you want to place an inductor, you call C.
Okay.
Capacitor, you call C.
Okay.
Okay. So now R underscore, okay. Now you can keep one R means it's a resistor, okay.
Yeah.
But let's say we have to identify this resistor, right? So there will be multiple resistors in your PDN network. So there's RBR, RBR. So how do we differentiate? So you give a name for the resistor. So let's say we call RBR, R voltage regulator. Okay. Then we say A, okay, or we can say node A. Anything, you can name anything. There should be no space, that's all.
Okay.
This is the first node. Node A. Okay, node B, right? Underscore B. We put a value. So let's say we say 1 milli. One small limit.
Okay.
One small limit, that's it. So that's basically what you've done is between node A and node B, right? You've connected a 1 milli resistor.
Okay.
Similarly, if you want to do inductor, you'll say load LVR. Node underscore B, okay. Node and it's case sensitive, remember that. All case sensitive. Node underscore C, and let's say we call it at 1.5 nano Henry.
Okay.
So what you've done is, and we want to hook up the voltage source, right? So we'll hook up the, let's say we'll hook up the voltage sources. You call V, okay. V underscore VRM, right? Node A, and then between ground. So ground is called 0. That's how you signify ground potential.
Ground is always 0.
So that is how by putting 0. Yeah, 0 is like we are telling it's ground potential.
Okay.
The 0 basically.
Okay.
Okay, I will tell that later as well. So 1 volt. That's all. 1. So if you want 1, it's a 0.85 volts. So that will be 0.85. That's all. So that means what you've done is you have supplied a 0.85 voltage supply. And you connected a resistor between node A and node B, and inductor between node B and node C. That's all. Like basically, I mean, I swapped it here. Yeah, you're getting. Yeah, basically, you have done this. So yeah, we can just. If you want to do this. Okay. Basically, this is what I did. So I have done this basically. So this is like the basic. So this is how you build any simple. If you want to build RL. So let's say I want to add a cap here. Okay. So cap is again similar. Okay. Very simple. So we put VR. Okay. Node underscore C, right? Because
between C and ground. Okay.
C and then ground, and then you can add some value, 1 microhenry, 1 microfarad, 1 U, 1 nanofarad, 1 picofarad, whatever.
Okay, fine.
You can put whatever value you want to. So remember, it's case sensitive. So very important is nano is right. Pico is small p, P is small pim, micro small u, mega is big M.
Okay.
So there is this. So it's all case sensitive. So giga is big G.
Okay.
So or else if you want to avoid this full confusion, I'll simple scientific. 1 e power minus 9,
Yeah.
1.5 e power minus 3,
Okay.
or 1 e power minus 12. Directly you go to your numbers itself. You can avoid if you want to avoid any risk, right?
Yeah.
This pico, milli, nano. I would suggest this is a good way as well.
Yeah, that is it.
Yeah, again, your preference, your style, whatever you want to.
Okay.
So now let us say in the real how you'll actually be building. It's a little bit more fairly more complicated. How you'll actually build it in the actual Intel deck, in how you'll be doing now in Intel.
Okay.
So what? So as you can see, if you can see my screen, you can see the power delivery network. Right? So this is like a first order simple power delivery network. This one we use this. So if you see, you will build one. So you so as I said, we only focus on from the inductor. So we do not focus before the inductor. So we give a voltage supply. Okay, we will hook up a LVR RVR. Now from this portion, right? From this portion of the from here, right? Basically from here, okay, till about here, right? This portion, okay, this is basically board plus package.
Okay.
This is the board
plus
package. Huh.
Okay.
So what happens here is, so either there will be two ways you'll get this, okay? So either you will merge it in the in the power SI itself, okay? You will merge both the board and package, like I showed you during the power SI training, and you'll extract it together, okay? Which most of the times will happen like that, okay? Or else sometimes you may have to extract the board separately, package separately, and connect it between board and package, which I don't need to discuss now because most of the times it will be board and package, you'll get it together.
Yeah.
Separate thing is there, we can discuss that later as well. For now, that will be a little confusing.
Okay.
But for now, I will focus on board and package merged together, which is what you will always see most of the time.
Yeah.
So, first I'll talk about that. So in this, so this will be in the form of an S parameter, right? So this is generally in the form of an S parameter, okay? Or else it will be in the form of a circuit file.
Okay.
Okay. In the form of a circuit file. Either it's SPAR or a dot circuit file. Okay. So first I'll talk about the S parameter. Okay. And then I will talk about circuit. So basically this is in the frequency domain. Okay. This is your characteristics and this is time domain.
Yeah.
Okay. So basically what we do in power SI is we extract this, okay, and then we convert it into this. Because we have to do two types of analysis, as I would have told you. One is a frequency analysis and one is a time domain analysis.
Yeah.
Mostly you will be involved in this. This is what is the most of an analysis will happen. The time domain. Because generally frequency domain is just to extract the characteristics and then we convert it time domain and then we done it. Okay. So as I would have told you, so this is how it works. So you have, so this part is S parameter, okay. So and then you have the die collaterals, right? This is the R die, C die, right? And the current, the sink, the current source, the sink at the final end after the R die, C die collaterals. If you have noticed in your deck, right? I will just open. I'm not sure. Do you remember the deck which we did for the synopsis? You remember the deck, right? So you had a bunch of R die, C die.
Yeah.
And then you had one current. Yeah. Okay. So if you, I will go there. To understand what we mean by that. Okay. First, I'll explain this part, and I'll go there. So okay. So now this S parameter. Now this S parameter, right, or dot circuit, right? So I will first explain that what it means and. So basically what happens is, see, we do two kinds of analysis, right? So we do a frequency domain analysis, right? Wherein we find the A in SPICE, right? Wherein depending on different, so you can see here, as if you notice this, so depending on different stages of your PDN, right?
Yeah.
You will have different behaviors. of your impedance. Your impedance varies for frequencies, and also because at different stage of your PDN affects at different frequencies. So your board capacitance affects here, your package capacitance affects here, your die capacitance affects here. So this is the same. So let's say you have S parameter, okay, and using S parameter in the frequency domain, you can do the analysis. But if you have to do in the time domain, right? If you want to find in the time domain, right? Like this, in the time domain, you want to find out what is your what is the behavior of your this is better. So what is the behavior of your power delivery circuit, right? When you apply a given ICCT, a different time domain circuit. See what happens is, so let us say in power DC, right? In DC, when you are doing DC, you are applying a 1 amp current sink at the DC, at the sink, right? And then you're seeing what is the drop from the source to sink. So similarly, but actually in real world, the current is not like 1 amp DC always. It will vary, right? So let us say it may vary from 1 to 1.2 up and down. There will be some. So for a given operation, there will be the switching. The current will switch, right? So the vendor will give us a typical, that is called an ICCT, that switching current. Okay. So the vendor, we will find out what is his operation. Okay. For a given operation, he will choose a set of operations, maybe like read, write, read, or something like that. He will look operation, and then what he will do is in his tool, right? In his tool, he will see it at the bump at this part of the PDN network, right? Where is that? At this portion, right? At here, at the bump, right over here. The bump. What is the current? What is the current seen there? Okay. Depending when I run, he will run in his circuit simulator tool. He will run a full-fledged operation, and he will see how is the current varying at this location. Okay, he will probe and check here, and he will give that current to us, which will look like this. Somewhat like this, something like this it will look like. So you can see it's idle, then some operation happens, then again it's idle, then some operation again is happening. So let's say it's idle, and then some read operation happening. The current is varying. There is some switching action. Then it's again idle. Then again some operation. So you can, so like this for different domains, for different bumps, right? Per, let's say you have in synopsis for your tool. So we have discussed VDIG, VP, VPH, and VPTX, right? So for all three, at like say one lane, one PCI lane, one VPTX domain, for a given operation, he will decide. He will just decide. It's not up. It's up to him. It's up to him for, because he wants to. He will decide what is needs to be designed for. What is my worst case current, which we can see, profile which he can give. And depending on that, he will provide it to us like this. So he will see how the VPTX domain varying for a given some profile, some kind of profile. Like that for each domain, he will give us the profile. We have to apply this profile, okay, at the end, at this end, at the same, right? So instead of just a 1 amp current source, DC, like a normal, proper, constant current source, right? We will now apply this constantly fluctuating current source. This is basically current. This is, imagine a current which is constantly fluctuating, right? So it has average value of 8 amps. Okay, 8 milliamps, but the value is constantly going from 12 milliamps to 2 milliamps, right? Imagine, just imagine it's going up and down, up and down, up and down. So imagine instead of providing like a 1 amp current, we will hook this up as a current source. Okay, which I will show you how to do it in SPICE. How do you hook up a profile like this? So then we will study. So this is how our, if you see the output, right? So this is how your waveform output we will see. So for a given output, right? So wait, I will take some example and I will show you. It will be more easier. Give me a show you some direct example of current versus voltage so that you will understand what exactly I'm talking about. So this is a voltage, okay? So for a given, when I applied a given current profile, okay, at the bump, This voltage this is the voltage I am seeing for a given time domain, for a given time duration of 40 nanoseconds. Okay. Now I will show the current profile. Okay. I will try to find the current profile. It will be okay. So if you can look here, can you see my?
Yeah.
The current which I'm giving. Okay. And this is my voltage supply which I'm probing. Okay. So this is the current which I'm supplying over here. Okay. At this portion. Okay. This ICCT over here. And this is the voltage also which I'm probing over here. I'm probing over here. Okay. And this is my ICCT over here. Okay. This is the current which I'm giving. The yellow color wave. Okay. So as you can see, the current has got a profile. Right. It has got a pattern. So it has got some busy time, then it's got like a no operation time, then it's got a busy time. And the value is also varying. So you can see it starts at 400 milli, it goes from 1.2 and comes down, 10. So I am supplying a 1.35 volt. That is my average DC voltage, right? So if you see, when I supply a average DC voltage, okay, DC VRM 1.35 volts, on an average I am getting I'm getting 1.322. Okay, 1.32. But on this, I'm getting some fluctuation. Right? This is the average voltage, which is seen. You can say like this is kind of equivalent to a DC drop, right? But on this, I'm getting some fluctuation, right? So this fluctuation also, you have to account into your design. Because, because what happens is, let's say this transition. So if you see, this is going from if you look at this time, compare this time zone, right? So if you see here, at the 10th nanosecond time, you are going from a very high value to a very low value. And if you see at the same time, my voltage is spiking the most. So it's going like from 1.32 to it is going to almost, if you see here, it's going to very high value. I will just click here. It's going to 1.35. It's almost almost 30 millivolt jump. Boom, it's going up. Because of just this transition. And if you look here also, see, it's flat until here, until this transition happens. From here, from very low value to very high value. Again, it's going down.
It is going down, yeah. Right.
And if you notice here also seeing a similar transition. From a very 400 millivolt, when it's going to very high value, you're seeing the spikes, right?
Yeah.
So you can see this kind of behavior we are seeing. So this is what is called an AC spec. Okay. This plus, so what that designer will tell is, the IP designer, he will tell, if I supply 1.35 volts, right, plus or minus 3% is your AC spec, he will tell. So if you say plus or minus, let's say plus or minus 2%, he will tell, okay? So 1.35, if you say plus 2, if you say 2% means it's around 40 milliamps, okay? Around, no, sorry, 27. No, I will say 3%. Plus or minus 3% he will tell, okay? So 3 divided by 100 into 1.35. It's roughly around 40 milliamps. Okay, 40.5. So 3%. So if you say plus or minus 3% means, see your peak to peak, right? 81 millivolts is your the burst. So what he's basically telling is your peak to peak difference is there, right? That cannot be more than 80 millivolts.
Okay.
So if you see here, my peak to peak difference, right? So from this is my lowest ever peak, and this is the highest ever peak over here. This should not go more than a given target. Some AC spec. So plus or minus 2%. So doesn't mean it should be like 40 plus, below also 40, above 40. Totally it should be 80 millivolts. It should never cross. Your peak to peak voltage. Okay. So this is this important spec, which we look in time domain, which you have to see in time domain. Right. So this is only one time. So for a given time, when you apply a current profile and you measure the voltage. So how do we reduce this? So the issue is, let me see if I have some. AC spec. Give me a minute. So what happens is we will see how our capacitors are playing a role. Okay. So this is where it can come into a role to controlling this peak to peak noise. Okay. So this is the frequency domain curve which we spoke about, right?
Yeah.
Which I told you AC analysis. Okay. So I will just change the color and I will make it thicker so that you can see it. So if you see here, you have a bunch of you have the mic frequency for a given place, right? It's varying from for a given node, okay, bump location. It is varying from 10 to 1 giga, 2 gigahertz, and it's varying starting as low as like 14, 15, 12 millivolt. Okay, you can notice it over here. You will see the impedance varying over here, and as you can see, it's varying. It's going up. It's going to about 20 millivolt over here, and then it's reaching the peak which you were saying at around 400, and then it's coming down. So if you notice here, right? So if you compare it to this, right? So if you compare it here to here, it's somewhat similar to this, which you are seeing over here. You are seeing the same thing, something similar you're seeing here, right? So going down, you're seeing that bump. So this part is affected by board. Then you get the package comes into play, and then my capacitance is coming into play. So what happens is, depending on the current which you get, right, the profile, the current which you get, your current will have different frequencies, components. Okay, you're given current, right? Whatever time domain current you have, it has different frequency components. So if you look here, when I run an FFT, I will just FFT. So forget the starting part, okay? So if you notice here, right? So if you notice your current for different frequencies, right? For different, let's start from 100 mega, okay? So for different frequencies, right? Your current has different amplitudes. That is the amount of maximum amplitude seen in different frequencies. So your at the same time, your impedance also has different frequencies. Has different impedance. So basically, see, when you multiply these two only, when you multiply your current into your resistance, you get your voltage drop, which is you're seeing over here, right? So by using capacitors, you can reduce your impedance at certain areas, okay, which have where your ICCT is the most impact in, okay, thereby trying to reduce this plus this total noise. You can reduce the fluctuation seen over here. See, basically what happens is, basically if you see in real world terminology, when your bit, let's say at the die level, it is switching from 0 to 1, okay, so that is, there is a sudden your drawing of current, right? There your chip is pulling current from the, now the distance, right? I mean, imagine at the speed at which your chip is switching, right? Your chip will be switching like some 10,000 times in 1 second or something like that. It's switching so fast, 0 1 0 1 0 1 0 1. But it's because it's switching so fast, right? It takes time for current to flow from here to here, right? It takes time because there is loss and it's not, you cannot flow that fast. So what you do is you add capacitors to act like a temporary charge storing temporary battery. So what happens is, when it's pulling current, momentarily it will pull from here. This capacitor will provide the current. By the time this cap will charge this cap, then this cap will charge this cap, this bulk cap will charge this cap. By the time VRM will charge the bulk cap. So just for that few nanoseconds before that thing is happening, before the VRM can take over, these caps and all. So what happens is, this droop is there, right? So when you do in time domain, so you are seeing this droop, right? Check this first droop. When you're pulling the droop is there, right? This droop will reduce. You will see a lesser droop because that first drop you're seeing, right? Because what happens is, imagine you're pulling the current full speed, okay? you're starting at 1.35, you're pulling the current, you're suddenly sucking so much current, but you're not able to meet that voltage because there is it takes time, right? It's suddenly pulling 20 amps of current, right? It's suddenly pulling 1 amp, 2 amps. So there's a drop. This drop comes. So you want to reduce this drop as much as possible. You want to keep it as stable as possible, the voltage.
Yeah. Okay.
So that's where if you put cap, we say cap reduces noise, means basically the impedance comes down, right? The impedance is coming down. When you add cap, so you can come down, right? So you're seeing this, your inductance, your package inductance, board inductance is going up, and your package caps are playing a role. So if you see here, this is the best diagram to explain. So if you see here, your board is coming, right? You have your board, capacitance of the board is playing a role, and then your board inductance is starting to take over, right? Your board inductance and all are starting to play a role, right? But the package capacitance is coming.
Yeah.
Immediately it's bringing it down. See, you know the basics, right? So capacitor always starts like this and goes like this, and inductor starts like this, right? This much. This. Yeah. So imagine, so the inductor is starting off high, right? It will keep going like this. Hey, if it's late inductor go, it will go like that, right?
Yeah.
So then you bring a capacitor and you bring this value down.
Yeah. Okay.
And if you know basics of your Bode plot and all that, this comes effective. Like it comes like this, right? So similarly, again, your package of LSC, right? So your LSCs are coming here, okay? But it has to still go from the bottom layer of the package to the top layer of the package, no?
Yeah.
So there are VRs and there are some traces which will add inductance and resistance, right?
Yeah.
So that is leading to this huge increase, okay? After capacitance, which is being brought down by the die capacitance after one frequency, because the die frequencies are die capacitance such a small value like picofarad and nanofarad, no? They can only act at a very high frequency, like maybe close to, if you see here in my case, die frequency is only coming up to 200 megahertz, almost 150 megahertz only it's coming in.
Yeah.
The die frequency, that effect is coming. It's coming down. It's the impedance is coming, right? So if you see the effect, if you see it's bringing it down so high. So from such a from 150, it's bringing it down to such a low value, right? So this is the impact of the die, But the problem is this portion is not designed by SPI engineers. This comes from the IP guide, right? So we have to live with what here. But what we can change are the board capacitance, right? We can change the board capacitance and the package capacitance. So by varying the values of the board and package, we can reduce this impedance. We bring down this impedance as much as possible, right? By bringing this impedance as much as possible, right, at different frequencies, when you multiply it by whatever current you get, right? When you multiply it by whatever current, your eventual voltage is less, right?
Yeah.
Your voltage swing is less, right? The voltage drop. So our aim is to kind of reduce the impedance. So let's say at 10 megahertz, now it is 20 milliohm, right? 18 milliohms. If I bring it down to 10 milliohm, whatever current is passing through, the drop will also reduce, right?
Yeah.
So let's say 1 amp current is flowing here, okay? At 10 megahertz. Currently the impedance is for 15 milliohm, right? But if I reduce it to 10, so I'm saving 5 milliohm drop, which will help me over here, right? Because if you see your voltage, if you see even your voltage, right? The voltage which you see, and if you if you want to check this in frequency, voltage also has characteristics. At different frequency, you will see different levels of drop.
Yeah.
Right? So if you see here, if you just ignore the starting before 100 mega, right? So if you see here, my highest drop is seen at after 100. And why is that? Because after 100 mega only I'm getting my highest impedance.
Yeah.
So obviously water through here, right, at this frequency, you will see most of my drop is at that time. And then if you see, as I keep, and you say at lower frequencies, it's a little bit lower it is. Below 100 mega it is low. And if you say after that also it reduces dramatically. Why? Because the current after that is also low. After 1 giga it's relatively less compared to, let's say, at 100 mega over here, maybe before and all. So what happens is, though the current is so high here, right, at 1 giga, right, but because the impedance at 1 giga is so low compared to the impedance at 100 mega, above 100 mega, 100 mega is dominating compared to 1 giga, if you notice here. The drop seen after 100 mega is dominating over the drop seen at 1 giga.
Yeah.
Why? Because the impedance is so huge at 100 mega, 150 mega.
Right.
So this also helps. So if you improve your package routing, right, how you go from, I explained, right, you want to go as vertical as possible.
Yeah.
You are the PA engineer, your aim is always to go as vertical as possible. You want to go from here to here directly. You want to go like this. You want to reduce this like this. You don't want to go like this.
Yeah.
You want to go directly like this. This is your preferred way. You don't want to go like this, then come left, then come up, then come right, then come up, come like that. You don't want to go like that.
Okay.
So you want to go directly. So that's as much as possible, you go straight up. By reducing this path, right, the path from the package base to the package top, you will bring down this impedance dramatically. You can bring this down. You will actually see. You can bring it down. And because capacitors also, because of the capacitor's position and the value of the capacitor which can be used, you cannot maybe always have effect at these frequencies. It will maybe stop. Package cards stop at this frequency.
Okay.
More than this, very difficult. After 20-25 megahertz, package caps will not have an effect because of where they are placed.
Yeah.
So this is what you do in time domain. So in time domain analysis, you will be looking at your ICCT profile. You will be it in the SPICE deck. You will look at the noise profile. You look at the output voltage. You will look. So when they tell not noise profile, this is what they mean. Sometimes they will use the word noise profile. This is what they mean.
Okay.
And this is the peak to peak noise. When they have noise, they tell what is the peak to peak difference. That's what's called noise.
Okay.
This is the switching noise, basically.
Peak to peak difference.
Every time they're switching, there is some fluctuation.
Yeah.
Because every time, this is called switching noise. Every time your chip is switching, it is causing fluctuations. This, why is it called this means? Because whatever fluctuation you see here, right, it affects your signals, the signal integrity.
Yeah.
So if there is a delay, because there is a delay to reach the from 0 to 1, if you're transitioning from 0 to 1, right? But due to the PDN network, it takes time, right? So when you go transition, see, if you want to actually transition, we want to go like this. We want a straight line from 0 to 1. But actually, it goes like this. The transition of from 0 to 1 is more like this rather than just a straight square wave, right?
Yeah.
Because it takes time to go. It takes time. Time, this capacitor. So this time, right? This delay is called jitter. This jitter which they will tell. You will say in SI, Pankuri may use this word jitter. This time. So you are expecting your one value to come here, let's say at 1 picosecond, but your one, it's becoming 1 only at 1.5 picosecond. Why? One of the biggest reasons will be because of this droop over here. Because of the time it's taking for it to charge, right? From 0 to 1.5. 0 to 1 is affected by how fast you can provide that voltage without much of a loss, right? Without seeing too much of a loss, how fast can your voltage go from so this fluctuation?
Yeah.
How much less fluctuation? How much less? So if you can reduce this fluctuation, that much faster it will switch, and that much less jitter you will have. Okay. So all your systems have a tolerance for that, right? So in real world, you are building a tolerance. You are like a designer will say, okay, up to 1.5 picoseconds, my system can wait and wait for it to become one. More than that, it will skip it. If sample at 1.5, it will miss it, right? So that jitter is modeled in, and by that, in reverse calculate using some formula, and they'll find out what is the peak to peak noise, for which you can get an acceptable jitter.
Okay.
So this is why they call it noise. Noise. So this term you will hear. So this peak to peak is very important. So that is why most of your analysis will be done in a time domain. Frequency domain is more like a reference, like I told you. You look at what is done in the frequency domain, right? You look at the impedance in the frequency domain, compare it to the current profile of the 50 of the current you get, right? The current profile. And depending on that, you design your PDN solution to get the least amount of noise. That is what you're doing in SPICE. That's it. So for this, what we do is, we do not, that is why we form ports on the capacitors. We form ports on the cap. So if you look here, I will take the SPICE network. Now I will show you how we build a SPICE network. So first thing is, so if you notice, you will I have listed something called x underscore VCC DDR. Okay. So this is how you list. So this is something called a subcircuit. So I will open one file for you before. So a subcircuit is a very important what do you say? Part of a SPICE of HSPICE. So let us say you have a RLC circuit network, okay, which you want to repeat, repetitively.
Yeah. Okay.
Right, like the C day, R day. You will repeatedly hook it up in different places, right?
Yeah.
You're going to hook it up to different bobs. So you can, instead of every time hooking it up like this. So let's say you want to hook up 1 nano, 1.5, 1 milli here, then again repeating LVR underscore 1 node A, again node D underscore, like you want to, the same RLC network, you want to hook it up again and again. You will say between these two nodes, hook up this RLC circuit.
Yeah.
Between these two nodes, hook up these two RLC circuits. You want to do like that, okay? So what you will do is a subcircuit. So first you define it by dot circuit, okay? You come up with a name for the subcircuit, right? So better I will use is your dial collateral, so that that will be you will be able to understand that also. Give me a minute. Tell me when you can see your dial collateral. Can you see it?
Yeah.
Yeah. Can you see it now?
Yeah. No.
Yeah. Okay. So you can see. So this is all subcircuit. So you have something. First, you have to type the word dot subcircuit. Okay. Then you have the name of the subcircuit. This can be anything. You can put whatever you want to. So you can write my subcircuit, my underscore HSPICE, my subcircuit. Okay. No space. Remember that simple thing. Underscores are allowed. Then you write the two nodes on the outside. Okay. Two nodes, which it will be connected. So let us say your subcircuit is like a black box.
Yeah.
Okay. You will have two nodes, or it can be three, whatever. You can make multiple nodes. Okay. Let us say for simplicity, we'll take two nodes, which is what generally it is. Okay. So you have two. Okay. Right. This is your subcircuit. You will have two nodes, A and B. This is what the outside world will do. They will just hook up their A and B to this A and B, and automatically the subcircuit gets hooked up to that. That is what they assume. Your subcircuit is like a black box, which only you know. So let us say we are having a and B. Okay. Now we will just put RC circuit. Okay. RC circuit. So it goes from A to B. Okay. All right. And then from A to ground. You're getting my point? Yeah. So you have from A to B. So you have, from A to B, right? You have A, B. So you have a resistor from A to B, and then you have a cap over here. Okay. So now, actually, yeah, this is not that good. Okay, we will do this. We will hook. So that is all you have. Okay. So this is let's say this is C1 and this is R1. Okay. So to the outside world, they only know these two portions. Okay. So they can hook up anything over here. So you can say that you can hook up anything over here, A and B. So what will happen is when I want all this in my into my deck, right? So this is a sub-circuit which I will define, okay? And let us say when I want to call this in my main deck, when I want to use this sub-circuit, so then what I will do is you first use the word X. X is the common thing, okay? If you want to define a circuit, you use X. Okay? X. After that, whatever, you can put underscore 1, okay? Whatever, you can write a word also. Then what you will do is you will write the wait a minute. You look at the okay, 1 minute. You will write the first A deck, right? So let us say A and B. You have to write the two node names. So let us say I want to my deck. It's called node A. Okay. My deck. It doesn't need to be the same. What is the equivalent over here? What is the equivalent to this position? Okay. So where which node in my deck I want to hook up A? where I want to hook up this A, okay, and I want to, I will say node B, okay, okay, and then I will call the subcircuit name.
Okay.
This is how you hook up a subcircuit.
Okay.
So automatically what happens is between this node A and node B, no? So node B gets translated to this A, node B gets translated to subcircuit B, and between this automatically between node A and node B, this R, B and C will get applied.
The circuit you mentioned there.
Automatically, automatically gets applied.
Okay.
So similarly,
and X1 name we have to give like anything or
X1 can be anything. X is to signify you are calling a subcircuit.
Okay.
That is, you are defining you are calling a subcircuit. Okay. X, you have to start with X.
Okay. Other than that,
so let us say so let us say we want to hook it up to another two nodes. So we'll do X2, or we can say X underscore another something, whatever.
Okay.
So X2, okay, node C. My subcircuit.
My subcircuit. Okay.
All right, like that. You can hook it up to multiple nodes.
Okay.
So you have just defined it once. So across multiple nodes, you can just. So similarly, when you are given an S parameter, right? An S parameter, which we are converting to, let me just see which S parameter I used here. Give me a minute. Open this S parameter. So this is a circuit file which I told you about, right? So I will just show you an S parameter and I will show you a circuit file, both, so that you will understand the difference. First I will start with S parameter and then I will go to circuit file. I will just open all these files and keep it. Okay, at least here. Okay, we will keep circuit file only. Okay, I'll first show circuit file first for you. So this is a circuit file, okay? This is a circuit file which you are used, okay? So first thing is when you are including any external files, right? When you want to include this file. So this is my main deck. I am now going to build this PDN network, okay? So I'm going to build this. I'm building this full network, right? So I'm going to be using first an external file which is called a .cir file. So this is how you first include, like it is like attaching, trying to say that this file is going to be included part of my main deck. It's in a separate file, but it's in the same, within the same folder. So this is how you see .include. You write the file name, okay? And then you come down. I will explain these definitions to you. Then you start with X because it's a circuit. So you start with X, subcircuit file, X underscore some name, okay? Then we start listing. So if you remember in PowerSI, I would have formed ports, right? Different ports. So I have formed some capacitor ports, then I would have formed some package capacitor ports, then I have formed some board ports, and then I formed some bump ports. And then I finally formed a VRM port, right? So what we will do is, you have to keep the same. So one important thing, both for S parameter and circuit file, right? The order of the port should not change. Okay, the order. So let us say board 101 is the first port here, right? Is the first port here. Port 1 is BR, or the first, not first port, and this is the first port seen, like it's the first port you see. BRDC 10198. That is that same one should come over here in your deck. You should call this, instantiate that port only over here in the starting. The name can be different. If you notice, it's port 1 underscore something. I have removed everything and just kept BRDC 10198. The name can be different. Okay, this is kind of like if you've done programming, it is like calling the variable. Okay, this is like a function, and I'm not sure. Do you have any programming experience? Basic.
Yeah, little bit.
Yeah, so it's like this, like a function, you can say. You're calling the function over here. The subcircuit is like a function, you can say, and you're passing a function. So like that, the order. So like I said, so when you look here also, right, in my example, A and B is there, right? I start node A and then you only define node B. Because in my subcircuit definition, I am looking for A and B, right? A starts and then B. So in my subcircuit definition, A node and then B node I have put on the outside, right? So when I connect a node A, right, node A comes here and node B comes over here.
Okay.
If I swap it, right? If I swap it over here, if I swap over here, right? Then node B node B will get connected over here, and node A will get connected, which is wrong, which is maybe not what we want, right? So similarly, this also follows the same thing.
Okay.
The order should be the same and the number should be the same. So let us say I have so many ports, right?
Yeah.
So I have close to whatever 93 ports starting, not 93. I have close to 81 ports, right? 80 ports I have over here, right? The same number of ports should come over here. Okay, till here. This see, because what happens is the port which are here, right? They are depending on the order which they are done. They are directly values over here.
Okay.
Okay. So Spice doesn't care about name. It doesn't this and all, it doesn't care. Okay. When it comes to this port instantiation, it just knows first port is linked to this some value over here. Second port is linked to some value over here. Third port is linked to some value below that. So if you let us say you mix numbers, huh? So then whatever port characteristic you're seeing over here you'll be seeing over here. You don't want that, right?
Yeah.
See, your port you're forming at a place is because you want to know what is the S parameter at that given port, at that location.
Yeah.
So if you mix up the thing, then the S parameters get mixed up. Nothing will happen. It will not tell error. Okay. It will just wrong output. Yeah. So imagine you start with bump. Okay. You start with the bump ports. Let's say we start with bump. So we take Control X and we start with bump over here. Right. Sorry. So we put the bump. Okay. So then what will happen is whatever S parameter is being assigned for the capacitors, right? They'll get assigned to the bump now, which is wrong because there are different values. Bump is at a different location in the PDN network. So it will have a different value, which is wrong, right? So this order is important. So when you're instantiating your circuit file ports, the ports, right, into your main SPICE deck, you type X underscore something, preferably you write your rail name, whatever rail you're doing. You write plus. This plus sign is important. Plus. So basically what happens is this all should be written in one line. Like imagine like one large line like this. Like this. Okay, I want to write this. Okay. A, B. But due to just the sheer size of the number of ports, it to the next line and to ease of reading. So when you're bringing it to the next line, and because you want to make it part of the same command, right? You write this plus over here. Okay. So basically, you're telling it is not like another command. It is part of this command only. This subcircuit only I'm calling.
Yeah.
Okay. But I am going to the next line to make it easy. So I can actually, this subcircuit is there, right? This thing is there, right? This thing. I can even write it like this. So x1, no, like this. x1 plus node A.
And in one line for
I can write node B, okay?
Okay.
And then I can say plus and I can call this subcircuit. I can write like this also. This is what I'm doing. That's all. I'm basically doing this over here.
Yeah.
Okay. So you can see the order doesn't change. The number of ports doesn't change. That is very, very important. Okay. Then there is one extra feature which you have to add is this 0, which is a reference port. Okay. So this is specifically done for .cir files, okay, or S parameters, wherein your port is taken reference as ground, right? When extracting, your port is taken reference as ground.
Yeah.
So for the purpose of the calculation, you need to add this 0 over here.
Okay.
So you're telling the reference node, the reference port is ground. You're telling all my ports are reference to 0 potential ground. Okay. And then you have your subcircuit name. So in this case, that is this name. My subcircuit is there, no? I'm calling this subcircuit name. We're calling over here. So where do we get the subcircuit name from? If you come in your, if you come to the right side, if you look at your circuit file, right? Yeah. If you come down, you will see this portion over here. See, subcircuit one definition.
It's not moving
over here.
The screen got stuck.
Can you? Okay. Tell me when you can see my cursor move.
Okay.
Can you see now?
What's the typing?
1 minute. Can you see my cursor move? Kajal?
Yeah, finally. Okay.
Yeah, it came right now, right? You can see, right? My cursor moving. So in the dot circuit file, right? In the circuit file, when you come down, when you scroll down, this is starting. When you scroll down, right? When you keep scrolling down, something called dot subcircuit in the starting only in the interface port specification here.
Yeah.
Here, if you see, my subcircuit name is defined, similar to what we saw over here.
Okay.
Similar to what you saw over here. Can you see my left side?
Yeah.
Can you able to see a dual screen?
Yeah, it's coming little.
Yeah, it's coming up then.
Yeah.
Yeah. See this left, right? I wrote my subcircuit, right? In the same position, they have given some subcircuit name. This is generally because what happens is we convert from S parameter into this file, right? So the tool automatically takes the file name and makes it as a subcircuit name. That is okay. But that is immediate. But this is the subcircuit name which you will get. Okay. _s. Okay. Which is we're mentioning over here. If you can notice in my main deck, can you see my main deck now?
Yeah.
Yeah, in the main deck, this is where that name is getting instantiated.
Okay.
Kind of similar to what you have done over here. My subcircuit is there, no? Similar to that, you have done this over here, right? Okay. Is my deck still visible? You are able to see?
I'm able to see. Hello.
Tell me when you can see.
It's the
you can see. View. Okay. It's still here. Can you see my cursor move? I move my cursor. When you can see my cursor move, it's stuck.
Okay. Now it's moving. Okay.
Yeah, it's moving. Great. Okay, good. So let us forget this portion of the deck for now. Okay. We will move over here to the board capacitance. Okay.
Okay.
So now this is a very little weird part. Tell me if you are not able to understand. Okay. If you are not able to, I will go slowly. Okay. So now you understood the concept of a subcircuit, right?
Yeah.
You understood what is a subcircuit, what is it called. So now as I have told you, if you can see my PPT, can you see the PPT?
Just a second. Wait.
Yeah.
Yeah.
Okay. Yeah, as you can see, there are lot of caps which we have to hook up. Right? Yeah. There are a lot of capacitors generally in a PDN network.
Yeah.
And as I said, we take a specific RC model, right? Which we generate from a tool, and we use that in SPICE because we want a very realistic interpretation of what is a cap actually used in the circuit, in the actual board. Yeah. Right? So we generally, Intel doesn't rely on vendor models like Murata or whatever. We instead we generate our own models. We have a team which does the job. Okay. So if you look here, can you look at my can you see the notepad screen now?
Now.
Yeah, tell me. Yeah, okay. So as you can see, highlighted on the right side, you can see my cursor move. I've highlighted a subcircuit, right?
Having some delay.
Yeah.
Okay, now. Okay.
Yeah. Can you see I have highlighted a subcircuit?
Yeah.
Yeah. So forget the name. Okay. Just the name is a name. You just ignore that. You just assume it's a name. Okay. So you can see first this is subcircuit, right? He started. He's given a name for the cap. So if you can see Murata, the vendor name, 0204, 1 microfarad. Okay. That is the form factor, 1 microfarad. XLP, the form factor. Okay. And then some other temperature and end of life model. Okay. EOL. Okay. Then you have your node 1, like a node A, and node 2, which is the node 2, which you see over here, right? Okay. Wait, I will just, yeah. Kind of similar to A and B, right? Similar to that. So inside this 1 and 2, right? So let's say I double click on this 1, okay? Can you see me this 1 getting highlighted?
Yeah.
So if you say this 1 is connected to various RLC circuits. So 1 is connected to something called N3A and by resistor. Then it's connected to RL. So it's basically RLC packet. Okay. So it's like this. So basically to make it simple,
this one
basically
is the
like
node
this.
1.
One is the node 1. Yeah, node 1. Outside node 1, right? Similar to node A, which you see here. Similar to node A, this is node 1.
Okay.
Kind of, it's the, you can say the same thing. How we did node A over there, right? That is 1. This is node 2. Okay. So if you see what is specific or which is unique about this subcircuit, right? Node 2 is playing the role of ground. So if you see node 2 will be used everywhere, ground should come. So if you see a capacitor, right? Look at this cap value.
Yeah.
So cap is connected between one node and one 2.
Yeah.
So cap is always connected between some node and ground, right? That is why I always connect caps.
Yeah.
Similarly, if you look over here, it's connected to this cap over here. So everywhere wherever node 2 is used, it is only with capacitors.
Okay.
So what they have done is they have kept this as node 2. So the reason being, which is why they have not, they could have put 0 here.
Yeah, well,
they could have corrected it.
Ground
why didn't they do that? Why is because sometimes you are not directly connecting to ground always. So file new. So what happens is not always people will connect directly to ground.
Okay.
Okay. They will have a resistor sometimes, and then they'll connect to ground. That zero potential is there, right?
Okay. Yeah, zero.
So what they will do is they will name this. This is GD. Okay.
Okay.
They will name this node as GD. They will have 1 milli resistor sometimes.
Okay.
And then what they will do is they will say they will try it like this. So if you can see, you understood this circuit, right? GD 1 milli.
Define this one also, na? Like
so they will do like that. So they will say RGD, okay, and they will say GD ground, and they will say 1 milli.
Okay.
So instead of 2, you will hook up GD.
Okay.
Okay, but in our case, we are not going to do that in our sub-circuit, in our deck. Okay, so what happens is, if you can see our deck, right? If you see our deck, I will just come down here. Can you see my left side part of the screen?
Yeah.
So let me go down to some board 0603. So you can see here sub-circuit 0603, 22 microfarad, one, and there is some RLC circuit. Inside some random RLC circuit, forget about it. It is describing the cap model. So what I've done is, now I need to hook up this 22 microfarad, this port, BRDC 10715, right? Which is the port over here, which I've defined over here. Because I have formed this port on the cap in the circuit, which is 22 microfarad.
Okay.
So this port is, this BRDC 10715, if you go check in my board, it will be 22 microfarad. I have formed a port on that cap. Okay. I have disabled the component of power SI. I am not taking the whatever power SI model is giving me. Instead, I'm going to hook up my own model over here. Okay. Okay. And I'll take this one. 10. Okay. Something. Okay. 10175. Okay. So what happens is, first I'm calling X, right? So we'll move here. So first you're calling X, right? You're calling X. Explained, right? X. Then I am just keeping the same cap name as the name of the sub-circuit. Okay, BRDC, I've just kept the same name. Okay. Then it is going, so this is, then I am going to call the positive part of the cap. So this one.
Okay.
If I come here, okay. Yeah. So this 1. So I said, no, 1 is equivalent to the positive node and 2 is equivalent to ground.
Yeah.
That is the equivalent, right? 2 is ground. Okay. So 1 is my positive, which is connected to the port, which I want to hook it up to. BRDC 10715, right? Okay. That is the port. 2 is ground, right? So I have put 0.
Okay.
I hooked up 2 directly to ground. So what I'm telling is, in the black box, which is BRD, which is this 0603 22 microfarad, right? This model. Okay. I have 1 and 2, right? I have 1 and 2. 1 is getting hooked up to BRDC, okay? The BRDC whatever. 2 is getting hooked to ground.
Okay. Yeah.
And how is it getting hooked to ground? I'm putting 0.
0 there. Okay.
Because what is a cap? So imagine this is a rest parameter, okay? And this is your cap port. Port BRDC, right? So what I am doing is I'm hooking up a cap model over here, okay? And then I'm hooking it to ground.
Yeah.
So this is 1. This is
okay.
1 and 2. So the 1 is hooked up to the BRDC 10715, which is the port name.
Okay.
Right? And 2 is getting hooked up to ground directly. And 2 in my deck is, in SPICE it's 0. Ground is 0. So directly I'm hooking up this thing to 0. So what will happen is, when it's calling this sub-circuit, right? When it links up the sub-circuit, it will replace this 2 port with the 0, with ground. So automatically everywhere it will become ground. And it will process it like that.
Okay. You're
you see, different. So if you're seeing, right, you're able to understand, right? This is the main S parameter.
Okay.
I'm having multiple cap ports. So one cap port, I'm hooking up a sub-circuit, a capacitor sub-circuit.
Yeah.
The sub-circuit has two inputs, 1 and 2. One is the positive, 2 is the negative or 0, the ground port. To 1 I'm hooking up my name which I want to,
Yeah.
and 2 I'm hooking up to 0, which is ground.
Yeah.
So that is what I'm doing. So let us say I take some other. So if you see here also 0402 10 microfarad, right? So similarly, if you see here, see 10 microfarad, how they hooked it up? 06. So XBRDC 10633. BRDC 10632, right? This is the cap which I want to hook up to. 2 is 0, and then the cap name, which is over here, the sub-circuit name. So similarly, I've done. So similarly for package cap also I've done the same thing.
Okay.
So package cap has got its own definition. It's got some own definitions. So I hooked up 0204 package C9 because if you see here, I have package C9, right? So I have package C9. I hook it up from X package C9, X sub-circuit starting. We give a name, package C9. I give the package name. I hook positive port is package, negative terminal go, and I put the sub-circuit in, which is from here.
Okay.
So like that, this is how you hook up your different capacitors to the capacitor ports.
Okay.
Different cap models are hooking it up.
Yeah.
So as I explained, right? So it's like you have a big black box or circuit file. Both are same. Okay, just divide it. The circuit file. These are different caps, right? These are different cap models. 2, 3, 4, 5. So different caps are hooking up different.
Yeah. Okay.
Different models are hooking up.
Yeah.
Okay. And these models are basically sub-circuit in the form of an RLC circuit. That's all. So as I said, the purpose of sub-circuit is repetition. So see, here I have, if I have so many caps which I want to hook up the same cap value. So instead of typing this this thing again, this full RLC circuit, typing it over here and hooking up BRDC to R0, then RL0, then C1, R2, or C2. Because what happens is, let us say you have done from R0 to C2, I hooked up to this, okay? Forget this is a sub-circuit. I have actually done an RLC circuit, okay? Now when I come to hooking up to this port, right, I have to change the names again. I cannot use R0L1 because, right?
Yeah.
So, see, I've already, if I use RVR, CVR, so if you're hooking up, if you want to hook this up again, let us say, I hook this up. You're seeing this hook up here, right?
Yeah.
Now, let us say I want to repeat this thing again. I want to hook it between node C and node D. I want to do the same thing, right? Then what, I can't use LVR again. I have to say LVR underscore 1. Some other inductor name I should use. It's a different inductor. It's a different inductor between nodes. It's a different thing. So, but if you want to do, when you want to duplicate, repeatedly connect, right? When you want to keep reusing. We use the sub-circuit to reuse. We're reusing the same sub-circuit hook up to different models. So this is a very useful. So if example I'll give you here, look here. So what I was explaining is, if you notice here, very good example. So I am connecting a 10 milli and a 1.9 nanohenry, 10 milli. So what I have done is, for every bump node, right? Can you see?
No.
Yeah, okay.
Move your cursor.
Tell me when you can see a paint screen. Yeah, tell me when you can see a paint screen. Can you tell me when you can see the paint screen and then start. Can you see my screen? Okay, we'll do one thing, Kajal. I will stop presenting. Give me a moment. I will try calling in via my phone, okay? And then I'll start presenting. Let's see if it is fast. Okay, just be online. I'm trying to Skype via my phone. I'll try that 1 second. Yeah. call in because I'm doing audio and give me a minute.
Okay.
Yeah. Okay. Okay, I'll share my screen again. Tell me if it's still visible. I will share it again. Tell me if crashing. So can you see my screen?
No.
Hello, Kajal? Okay,
Yeah.
okay. Okay, can see it now. Huh?
No. Now it's
Can
loading.
you see the paint window?
No, it's loading.
Okay, then wait one. Okay, then just be online. 1 minute. I will just check something. Yeah. Hello, Kajal. Can you hear me?
Yeah, I can hear.
Okay. Now I will try to share my screen.
Yeah, your screen I can see.
So I've connected via the phone. So that tell me when you can see my screen.
Yeah, I can see your screen.
Is it visible now?
Yeah.
Yeah. Okay. So yeah. Okay. I'm on speaker. So if you want me to talk loud, can you hear me, right?
Yeah, I can hear.
Yeah. Okay. If you're finding it soft, tell me. I'll talk loudly.
Okay.
So if you can see my paint window. So in this, what I'm trying to do is I am trying to get connected 10 milli
That window
home register.
your PI training session for HSPICE mail window is open. I cannot see your paint window.
Okay, that means Let me wait 1 second.
Okay.
Let me share my screen again.
Okay.
Tell me if you can see it.
Okay.
Connecting. Here is something. Still connecting. Looks like it's going to take some time. Can you see my screen? You're not able to still see it?
No, blank.
I don't know. There seems to be some problem. I don't know. It's taking too much time.
Now again it went.
Okay, it came and went, huh?
No. It was coming like loading, then blank, then went.
Okay, wait. I started sharing. Tell me when you can see.
Okay. No. Okay. I can see.
You can see the notepad file, right?
Yeah.
Yeah. Okay. Tell me, can you see the paint window?
Yeah.
Yeah. So basically, we were talking about the usefulness of subcircuit, right? So because we can reuse a subcircuit, any complex subcircuit, you can just reuse it again and again. So let us say in this case, when a perfect example to show that is, so in this case, if you see, I have multiple bump ports, right? I have bump. Can you see my notepad? I have bump VCCP2, bump VCCP3. And both places I need to hook up a resistor of 10 milli 1.9 and I want to hook up a resistor of 10 milli and a capacitor of 1.9 nanofarad. So if you can see here, I have to keep R die, C die 3, then I have to change the name, R die, C die 4. So imagine I have like 10 bump ports. So then I have to keep repeating R die 1, R die 3, C die 3, R die 4, C die 4, R die 5, C die 5. So it just kind of makes it more and more difficult. So that's why we use subcircuits, especially when we have a very complex subcircuit like this. When we have something very, very complex like this.
Yeah.
We have multiple RLC connections. So, from the purpose of our PDN network, so what we have done now is we have taken you see my PPT?
Yeah.
Yeah. So we have taken the S parameter network, right? We have hooked up the package ports and we have hooked up the board capacitor ports, right? The board capacitor ports, right? The board capacitors we have hooked up. We have hooked up the package capacitors. You can see my SPICE deck. Can you see my SPICE deck?
Yeah.
Right. So and we have done this by instantiating the circuit file. We have instantiated the circuit file, and then we have hooked up the capacitor ports. Now we have to do two things. What are the two things? One is to connect the VRM.
Okay.
And one is to add the die collaterals. Okay. So in my case, okay, the die collaterals in the form of a lumped man, 10 milliohm and 1.9 nanofarad, nanohenry R die C die. So what I have done is to the bump ports, right, which I have named bump underscore VCCP2, right? I have hooked it up. I hooked up my R die and C die. If you can see here, R die, C die 3, R die, C die 4. I hooked it up.
Okay.
Okay. Similarly, LVR, RVR, if you can look here, LVR. So what I'm doing is, my LVR is between, let's say I have taken two nodes, node 1, node 2. I have connected a LVR of 4.35 nanohenry, then RVR of 3.3 milliohm.
Yeah.
Okay. Connected between node 2 and VRM. What is VRM? That is the VRM port, the port which I formed at near the inductor in the S parameter.
Yeah.
So you can say essentially, my VRM port is this. Okay. This is the node 1 and node 2. LVR, RVR. Node E, node 1. And this is node 2. And this is my VRM port. And here I am hooking up my 1.5 volt voltage source. which is what I'm doing over here. If you can see my SPICE deck again, I am showing it. I have highlighted it. VR1,
Yeah.
I'm connecting it to node 1.
Yeah.
Node 1 is where I connected my inductor. I also connected my 1.35 voltage source. So again, if you say how I've connected it, node 1, ground, 1.35 volts.
1.25.
So similarly, so see, voltage source, ground, node 1.
Okay.
So this is how you build up this is how you do it. Okay? Now, depending on what kind of simulation you want to run, you want to run time domain, or if you want to run a frequency domain, AC plot, right? This is where your portion will vary. From here, it will change. Okay? Now, if you want to run a transient, so how do you tell SPICE you want to run a transient? You first say dot tran. Okay? Then you put the sampling. So you are probing it at different. So you want to sample the output, right? So at what time interval you want to sample it? So we have taken 1 picosecond. Okay? And then 40 nanosecond is the maximum duration for which I want to run for. So this is what. If you see here, my output is for 40 nanosecond.
Yeah.
If you can see this graph, it's for 40 nanosecond. And this is sampled at 1 picosecond, the output.
Okay.
Okay, every 1 picosecond is sampling the voltage.
Okay.
Now, how do you tell SPICE that I want to see the output where? Where do you want to see the output at? Right? You can probe it at any port. You can probe at capacitor ports. You can probe at VRM port. But we want to probe it at the bump, right? We want to know what is the voltage performance at the bump.
Yeah.
Okay. We want to see what is the transient voltage at the bump, right? So if you see here, dot probe, right? Tran B bump underscore VCCP3. So this is my bump port. Okay. This part is common for everything. Bump. Okay, I'm probing the transient voltage at bump VCCP3. So like that, I'm probing at multiple locations. Okay.
Yeah.
Now, so this is how you probe. So what I'm trying to say is, if you see bump VCCIO3, right, and if you come here, you see it will come over here. VCCIO3 is being probed, right? Voltage at VCCIO3 is being probed. If you can see the screen, right? So what all are probed over here? No, VRD, DRAM, VDDQ, DRAM2, VDD, all of that has been probed over here.
Okay.
All right. Now, so okay. So for you, if you would remember from your deck, right? Your specifically your synopsis deck, okay? The current. So see, can you see this top power integrity? Can you see my cursor move? You can see it, right?
Yeah. You move it little bit.
Yeah.
Yeah. No. Okay.
Yeah. I'm highlighted. Okay. So as you can see in your, if you remember during our synopsis discussion, we spoke about different subcircuits, right? High-level subcircuits. Right? So this is one subcircuit which we found, which is a lane SIPI model, right? It is connected with its group, so it's called lane SIPI model, connected from ground, VP die and VPH die, right? So this is similar to the 1 and 2 which we saw over here.
Yeah.
The outside, the 1 and 2 which you saw over here, right? The 1, 2. Right, that is similar. This is analogous to that, right? The ground. So if you see here, they named this as ground.
Yeah, okay.
They have named the node only as ground. So they're giving you the idea that you should connect your ground port over here.
Okay.
So in our case, we put 0. We don't have a ground port. We don't have any resistor. We don't have any special ground setting. So we just put 0 there when we're calling this subcircuit.
Yeah.
So what will happen is, this ground is there. You have VP die. You have VPH die. Okay. And then you have some RLC circuit, which I showed in the video diagram, right? Which I showed you. Some RLC circuit which has been built. Now the current. So you have built this portion of the. Can you see the PPT? Tell me when you can see the PPT.
Okay. Right. Yeah.
Yeah. Okay. So you have this. You have built this portion of this RLC subcircuit, right? This R die, C die, RMS, some RLC RC circuit is given.
Yeah.
They have connected this. But how do you hook up this current? We need to hook up the current, right?
Yeah.
Somehow we need to hook up the current. So how we hook up the current is, first thing
thing is we hook up the current via C. We first generally hook up the current via another subcircuit. Okay. So PWL file we call piecewise linear model. Okay. So basically, what happens is this piecewise linear model is effectively a subcircuit itself. Okay. So if you wait, I will open this file. Okay. I need to open a couple of files. Give me a minute. Give me a minute. No. Okay, cool. Tell me whether you can see my cursor moving.
Okay, I can see.
Yeah. So if you look, so you focus only on the synopsis style because that is what you'll be working on. So if you see here, they have hooked up a certain RLC circuit, right? They hooked up some RC circuit. Some circuit they hooked up. And they've added this one statement called dot include lane underscore current dot INC. Okay. As you know, when you do this dot include means you're attaching, right? That is what this dot include statement is generally the role, right? Then you come to lane current dot INC. If you see here, I will move this to the other view, both of these to the other view, so that can you see lane current dot INC on the right side, my cursor moving? Yeah. So if you see here, it has got many subcircuits, right? Again, as I explained to you, X starts with X, some name, it's got BPH lane, which is one of the nodes defined in the top power integrity test bench, right? Then 0, right? Then it is got this lane and a VPH underscore X1, right?
Right.
And if you go to 1 minute, give me a minute, which is there is one more file which I need to open. This is what I don't like about synopsis. Yeah. So can you see my screen? Can you see my current cursor moving?
Yes.
Yeah. So you can see this lane underscore BPH underscore X1, right?
Yeah.
Which I have highlighted.
Yeah.
So that go search over here. It is somewhere that subcircuit is defined over here.
Okay.
Lane
BPH ground. Okay.
So if you look here, it's got subcircuit lane and BPH, right? Let me just move this over here, move to the other view, so that we can compare both. Okay. So you can see both. So you can see the lane current on the left, and you can see the current subcircuit INC on the right. Right? You can see them both, right?
Yeah.
On the left side, you are first calling the subcircuit X lane, right? X lane, you are calling it. You are calling VPH lane 0, and you are calling lane and a VPH underscore X1, which is linked to this file. Okay. Dot subcircuit lane underscore VPH underscore X1. VPH is ground. So to the VPH, he is connected to VPH lane, and to the ground port is connected 0. Like how we do it.
Yeah.
Right? Then inside it, what inside the subcircuit, he has called for some PWL file. He has included a PWL file. Okay. What is this PWL file if you go see? It's basically another kind of, it's basically you can say time versus current column. So the left side is time.
Time versus current.
Right? Start current. So time. So for 0 seconds, you have 1.3 milliampere.
Okay.
At 7.6 14, right? So this is like I think 0.076 picosecond or something. You have 1.3 milliamp. So example, so just to show it more easily, right? I will just open this in
graph.
In a file browser in the graph, so that you will be able to understand it. So we visualize it. So that's here. Let's see whether I can open it. Give me a moment. Take time. Yeah. So you see, they have given. Can you see my screen?
Yeah.
Yeah. If you see here, right, you can see they have given some waveform. This is how IGCT waveform looks like.
Okay.
Going up, down, up, down. It's starting from 0. It is going up to around 65 nanoseconds or something, right? It is starting from 0. It is going to around 65. You can see here 60 nano. After that, going almost, I think, 65 nanosecond. So if you open it in a text editor, right, and you scroll down completely down, so you can see the text editor.
No. Yeah. No.
Okay. Tell me when you can see the text editor. Yeah. If you see this is the PWL. And see at the last, right? The time is around 60 nanoseconds.
Yeah.
And some value is there. Some current value.
Yeah.
Right? So this is basically the current profile is hooked up in a convoluted way. Okay. So what they have done is they have attached it to subcircuit. Okay. So eventually this VPH and GD is there, right? It is getting cut to this VPH and GD. So what is happening is VPH and this GD. Right? So this VPH and GD, which you are seeing in current subcircuit.inc, right? It is connected to this PN0 over here. Okay, I just opened some random one, but it's connected to this 2 ports here.
Okay.
Right? Current is connected to this 2 ports. Okay. Now this VPH and GD which you're seeing here is reverse connected to this VPH lane and 0 over here. Are you getting my point?
Reverse?
Because this is linked to this, right? Can you see my screen?
Yeah.
See, I will start with the PWL. Okay. Can you see the PWL file?
Yeah.
So the PWL file, you have 2 nodes, VP and 0. Right? I've opened a sub. I will open a VPH one so that it will be. Tell me when you can see a PWL file.
Okay.
Yeah. So here you can see this VPH node and ground node, right? I lane VPH node and a ground node, right? So this is connected. So where is this being called? This file, right? This file is being called in this file. In this .inc file, it is being called in this subcircuit.
Okay.
This subcircuit. Right? You can see this file over here. It's big part. Right?
Yeah.
This subcircuit. And in this subcircuit, we are connecting that VP and 0 which we saw in that PWL file, right? We are connecting it to VPH and GD over here. VPH and GD is getting connected, right?
Yeah.
And where is this subcircuit getting called? This subcircuit is getting called in the left side. If you can see one more INC side, lane underscore current subcircuit, right? VPH lane. You can see my cursor.
Yeah.
Yeah. So this lane underscore VPH is called in this file. You are seeing, right? So this it's like subcircuit inside a subcircuit.
Yeah.
So they have circuit inside. See, first the PWL is in the form of a subcircuit. Okay.
Yeah. Then okay.
Okay. So this VPH over here is connected to the VPH lane. Can you see my cursor move?
Yeah.
This connection. VPH is connected to VPH lane and 0 is connected to ground. Right? And in reverse, if you go back to your test bench, if you go like back in reverse to your test bench, right? This VPH lane effectively, eventually through some RLC circuit, is getting connected to VPH die. I will open the video drawing and you will understand. Give me a moment. It will take some time for you to understand it. Once you build the subcircuit, right? You get with Pankuri and you build the subcircuit, build the full deck itself, you will kind of get. So as you can see here, can you see my video drawing?
Yeah.
So there is some RLC circuit, okay? There is some RLC circuit, and it's connected to 2 nodes, VPH die and VPH lane.
Yeah.
So what is happening is, to this VPH lane is there, right? To this, let me see, can I try to draw here? Okay, I'll just do this. So to this VPH lane, right? To the VPH lane over here, I'm hooking up that subcircuit at the PWL side. in reverse. I showed you, right? Inside a PWL file is hooked up over here. Okay. And in return, PWL file via some RC circuit is connected to VPH die, which is the value, which is the node you're seeing outside. You can see my test bench, right? You can see the. Can you see the?
I'm seeing. Okay, now I can.
Okay. Tell me when you can see the node. Yeah. So that VPH die, you can see here, it's highlighted on the left side.
Yeah.
Can you see VPH, my cursor move? So that is how.
Yeah.
So eventually, if you see via the convoluted process, they have hooked up the current to your VPH die.
Okay.
Yeah. So what happens is, so let's say example. So let us say example, we take this. Okay, we'll just use this. I will just use this as a way to explain. So I'm going to use this subcircuit and hook it up to some port. Okay. In my deck. Okay. So, but let me. So what we do? Can you see me type? See me type X?
Yeah.
Yeah, X. So I'll say X underscore PCI.
Okay.
Okay. Then so then we have first is ground, right? Ground is the first port. So 0. Right? Now let us say I'm going to connect VPH die. Okay. So that means I have no connection to VP die. So I can put some dummy port here. So VP1 underscore die. Make sure this is not an actual variable or put anywhere in your deck. Okay, this should be like a dummy.
Okay.
You can either connect it to ground, but I would say better just give a dummy name to it. VP1 underscore die or something.
Yeah.
Okay. Make sure this is not a port name or net name anywhere in your SPICE deck. By mistake also should not fit up over here.
Okay.
Okay. Then I'm going to connect a port over here, a bump port. So I'll say bump underscore PCCIO2. Okay. And then I'm going to call this lane SIPI model. Over here. That's it. Once you do this, right, what happens is, it comes over here. Can you see the second top integrity test bench?
Yeah.
So it comes here. So I ground I've given 0. So VPH die I've given some bump underscore PCIO, right? So from there it passes through all this RLC circuit, gets hooked up, and eventually the PWL file also gets hooked up, the current source. So what Synopsys has done is, with just one sub-circuit, he has combined everything and given to you.
Okay.
So he is like, when you want to hook up your die collateral, wherever you want to hook it up to, you just hook up this sub-circuit. Now you need to modify the sub-circuit a bit, okay, which Synopsys has given you, because what has happened is, in the lane current.inc, if you can see the lane current.inc on the right, and that side, can you see the test bench? Can you see that?
Yeah.
Yeah. If you see this lane current, they have called all the PWL files.
Okay.
Right? See, they have called VP. But in our case, we are not doing that, no? See, the sub-circuit, we will hook it up bump by bump. Right? Whichever bump port we want to, we'll hook up this sub-circuit. So now either it could be VPH, it could be VPTX, it could be VP, it could be VP die also, VP ditch, right?
Okay.
Depending on which bump it is, right? So if you see here, he has defined all of the exclaves, right? He's connected even this sub-circuit, this PWL, he's connected this PWL also, he's connected this PWL also.
Yeah.
But we don't want that. We want different sub-circuits where different PWLs are connected.
Okay.
Because, so what we will do is, we will take this deck, okay? We will make our own sub-circuit, okay? We will edit it a little bit we'll edit. Can you see this new one? Can you just tell me?
Yeah.
Yeah, 1 minute. Can you see new one now? And left side you will see lane current. My cursor is moving, so can you tell my cursor is moving?
Yeah, now I can.
Yeah. So we will take his sub-circuit, okay? And we'll edit it a little bit. So what we will do is, we will rename a sub-circuit to, let's say, VP, okay? We will call it, we will just say VP, VP, okay? Then instead of include all the PWLs in one sub-circuit, right? We will only copy the VP exclave, Okay. And we will remove this include, dot include over here, and we'll replace it only calling VP. VP underscore. So only the VP current is getting hooked up.
Okay.
So though there is a RLC circuit for all the other circuits, right? There's RLC circuit for all the other nodes. Only VP. This can you see the visual diagram?
Yeah. No.
Okay, tell me when you can see the visual diagram.
Yeah, I can see.
So though that one subcircuit has an RC combination, has all these 4 RC combinations, no?
Okay.
I'm going to only hook up current over here at VP name in this subcircuit. Because then only this will get excited. Only this excitation will happen. Others will not get excited. They are just as long as like remaining dummy. Right? And what I will do is in my main deck I will connect to the VP underscore deck.
Okay.
Right? Similarly, what I will do is I will make one more subcircuit. Okay? For VP ditch. What I will do is I will create a subcircuit for VP ditch. Okay? I will rename this as ditch. Okay? I will rename the subcircuit as lane underscore SI model underscore ditch. And I will copy this explain VP ditch from the lane current INC. And I will replace that with this explain VP over here. So you're getting my point. I am making like multiple subcircuits.
Yeah.
Okay. I am not touching RC connection. I am just hooking up different currents.
Current, yeah.
So what happens? So let us say I have a bunch of ports. So I have plus. So let us say I have a bunch of ports. Okay. So I have plus bump underscore VP ditch. Okay.
Yeah.
And then I have plus bump. I have a plus bump underscore VP. Okay.
Okay.
So then what I will do is I will say X VP1. Okay. Ground 0. This is ground, right? Because in our subscript ground 0. VP die. I want a VP die. So bump underscore VP. Right? Whatever. I'll just copy paste it. Okay. Then VPH die is dummy, right? I'm not connecting anything to it. Okay, so I'll just VPH die underscore 1. Okay. And then I will call this subscript.
Okay.
Okay. I call this over here. So you can see this layer underscore SIP underscore VP, right?
Yeah.
I will call that over here. So only VP current is getting hooked up for this bump.
Okay.
At that bump, you are only going to hook up the VP current. Similarly, I will do X V ditch 1. Okay. X V ditch 1. Okay. I'm going to call ground. Okay. 0. I'm going to call the V ditch bump. Okay. But V ditch is actually connected to VPH. Okay. So VPH, VPTX, and V ditch are all connected to the same node, and VP die is separate, right? So that means this has to get connected to this node, VPH die, and VP die. So then what? I have to enter one dummy variable VP. So VP die underscore 1, right? Some dummy variable. Then I will hook up my port, bump underscore VP ditch, and then I will copy this subcircuit.
Okay.
Over
Yeah.
Here. So this is how. So basically what you're doing is you're taking Synapse subcircuit, wherein he is done, for example, he has hooked up all the currents. And you are editing it and you're hooking up different currents for different subcircuits. So that different bumps will have only that much current only will.
Okay.
Right?
Yeah.
So that is what you are doing. So this is how you will connect it. So I think once Pankuri will build the subcircuit with the deck, right? It will build this deck for this one.
Yeah.
Pankuri will help you. You will be able to understand.
Okay.
I will also help you that time whenever you need.
Yeah.
But once you extract from outside and you build your S parameter deck, right? That's when you will understand, like exactly what you're connecting to what.
Yeah.
So this is how we are going to hook it up here.
Okay.
One few common important which I want to tell is, can you see my main deck? Can you see my cursor there?
Yeah.
So you would have noticed certain statements have a star in front of them. Right? Can you see a star?
Yeah.
So star is comment. So if I remove the star, that means I want that statement to execute. If I don't want it, I can just comment it.
Okay.
Otherwise, also if you want to write a comment, also if you say you start with something, writing a comment.
Okay.
We did if you understand. How you comment a like. That is how you start a comment.
Okay.
So if you put a star in front of a command, it's easier. You don't want to delete it. You're experimenting.
Okay.
You're checking right or wrong. You're doing all of it. If you just add a star, comment it. It will not execute that step.
Yeah.
Make sure always you end in your deck with .env and your subcircuit also, right? Your subcircuit. If you notice your subcircuit will also end with the .env and your .env and your subcircuit.
Yeah.
If you can see the right thing.
Yes.
So that .env is important. Not extremely important, but good.
Okay.
Yeah. So one very important thing in SPICE, which is going to be the weird thing, is how to include all the files, right?
No.
So if you see here, you are hooking up subcircuits from different files, all of them. So how to include a file is dot include. In quotation marks, you can include the file name, right? Dot include different files, txt files, files you're hooking up. When you build your deck, you understand which all files to hook up.
Okay.
And you can copy paste the full models, right? Capacitor model into your main deck. You can copy paste it.
Okay.
The definition, the model definition, in the starting of my deck. Before I start my S parameter definition, the definition of my everything. Yeah. So this is how. So if you look here, right, and I double click over here, right? Can you see the 7343 HP 330, right?
Yeah.
When I go up, the same thing is getting highlighted over here. That subcircuit is getting linked over here. So that's how. So that is going to be little bit confusing in the beginning, how to include and how to attach files. But once you start doing it, right, you kind of get a hang of what you're doing.
Yeah.
Once you start build a SPICE deck, it is very simple. Whenever you want to build a SPICE deck, right, immediately start drawing the subcircuit. You see the PPT, right? Draw a subcircuit. You draw RLC network in a paper.
Okay.
This is my VRM. This is my RVR. This block is going to be my S parameter. This is where I'm going to hook up. So if someone gives you a SPICE deck also, right? You trace like that. Okay, this node is connected to this node. At this port is hooked up this CAN. This is a capacitor port like that. The capacitor like that. If you build this subcircuit, right, you will immediately understand what is built on.
Okay.
So that is like you do that, yeah.
Okay. Yeah.
So start off like that. Draw it first, and then you can you will be able to understand. Draw it in paper. Sit and draw RLC circuit.
Yeah.
Kind of. Something like this. Don't need to draw too much complex. Just what is LVR, which port is getting connected to, like that.
Okay. Yeah.
Where is the port? What are my bump port? What is my RLC? What is how is this getting? So yeah, this is it for now. So I will share this deck with you. You are recording, right?
Yeah, I will record it.
Okay. Yeah. Okay. Cool. Thank God. So you can review this video. Okay. Once Pankuri starts building her SPICE deck, right, for your project, I think she will involve you as well.
Yeah. Yeah.
So you can work with her, and you'll better understand. You'll better understand what you're doing.
Okay.
Maybe I may also be involved in helping, but yeah. Once we start working on a SPICE deck, you will be able to understand. It may seem a little difficult, little bit different, lot of information now. Yeah, but once you do it, you will understand. It's relatively very simple. You can understand.
Okay.
So yeah, okay then. Yeah.
Okay.
That's it, Kajal. I will share. I don't think that I will share these two PPTs with
PPT
you.
also, no?
Yeah, these PPTs are there. These two PPTs. I will share it with you. I think these are part of the training videos which initially have. I sent you some training materials, right?
Okay, it's there. Okay.
So it's part of that.